Hi, this video will cover section 1.10, mathematical modeling and variation. So our objectives are listed here. We're going to use mathematical models to approximate sets of data points. We're going to use the regression feature of a graphing utility to find the equation of a least squares regression line. And we will write mathematical models for direct variation as an nth power, inverse variation, combined variation, and joint variation. So in example 1, we have a mathematical model. And you could see the table, it is represented here. And we have the population Y in millions of the United States from 2003 through 2010 are shown in the table. And I want you to notice how for the independent variable, which is the year, we're using the variable t. We're not using x. So when you enter your answers on WebAssign, make sure that you are matching the variable to the one given in the problem. So here we have the years. We'll go from 2003 to 2010. That will be the input. And the input of the linear model, and we have the equation here, the input is not going to be the whole 2003. It will simply be the year number 3, t equals to 3. And the last year, which is 2010, we will use the last 2 digits, so it will be 10. And you could see here how the linear model, which will be the equation given here, it is expressing that it could be considered from negative infinity to positive infinity, but for this specific one, they are restricting the domain from 3 to 10. And we have the equal to 3, so it says from the middle to the left, it says t is greater than or equal to 3, and t is less than or equal to 10. So we already said t represents the year. T equals 3 is the year 2003. So just like that, 2005 will be represented with t equals 5. So if we plot actual data and the model on the same set of coordinate axes, the question is, how closely does the model represent the data? So what I'm going to do is graph the linear model that we have here, and then we will compare both graphically, and then we're going to be getting a we'll be looking at the table. So I'm going to pause the video and get my calculator ready. So I typed the points that are coming from the table of values, and I also typed the equation of the model that we were given. And so as you can see, the model is represented by the line in blue, and then the table from here, the table here. So the y values that you see are the numbers that are here on the second row of the table, and they represent the population of the United States, and that is the dependent variable or the output. So we could see the it's almost like a perfect fit. And so for us to be able to get this type of view on Desmos, because if we were on a standard window, we wouldn't be able to see the line. So what you could do here to adjust your view is press this button that says graph settings. It looks like a wrench, and then it looks like a wrench, and So what I did is I changed the X values. So remember we talked about how the X values were going from 2003, which is the number 3. And what you could do here is you could even put a 0 if you wanted to. A 0 will be representing, I kind of like the -1 because I can see the y-axis. Okay, let's leave it like that. And then here, let's change this. The last year that we have is 10, so let's enter an 11. And then here for the y-axis, we could also change that. And we have from -1 to 320 because that was the highest, well, the highest y value that we have on the table is 308.7. So we could even make that into a 310 if we wanted to. And so that's kind of similar on how you adjust the view on a calculator. So we press enter. I'm going to make the keyboard disappear from here. And then if I click on the graph, I could see it that way. Now you could also drag it with the mouse if you hold the left button of your mouse while you're moving it, and you could do that. So you could see here we have the years. So for year 3 we have that point, year 4, 5, 6, 7, 8, 9, and 10. Well, actually we do not have one for 9. Is that? I think I just forgot to type it. Okay, so if I zoom in more on the line, we could see how the points are not exactly on the blue line. And so I'm just going to move the graph. So I'm trying to get to year 4. That's how much I zoomed. Let's see. There we go. So here's for the year 2004. Oops. The year 2004, and you could see the point is not really on the graph. Now let's find the number that corresponds to x equals 5 right here, or t equals 5 for the year 2005, and you can see how the point is below the line. Let's look at the other points. So that would be for the year 2006, and if I zoom in, you could see that it's a little bit off. The point it has, that's what the table was giving us, 298.4 million, and on the table, not on the table, but with the model, we get 298.32 million. So it's not too far, but I mean, when you're talking about million, perhaps it is a little far, the difference. And you could see that some points are above the graph, the line, which represents the graph of the model. And then other points were below. So they could be considered overestimations, underestimations. And so the model, the way here we can see one that is below. And so the model was found by using one of the techniques of the linear regression. And so what you do is you enter the set of points that you have, and then the calculator will try to find the best fit for those points. With the image that we see here, we could see how the points, some are above, some are below. But with decimals, you could see clearly which ones were above. So if we look at the table of values for both the original table that we had at the beginning of the problem, and those were the values that I plot as points. So those are the values that came from there. Now, the T value, the number that represented the year, that was the same for all. So that's why when I plotted the points, they had 9 comma and then the y value. So the y star is going to represent the model that we were given, and that is the equation that I entered here. So if I look at the table for both, we could see I'm here. I'm gonna just let's go ahead and change this. So I'm gonna enter the y values of 3, that was for the year 2003, and then 4, and delete that and enter 5, and then 6, 7, and then I can keep just typing x values, and then I can see the table. And we went all the way to the year 2010, so that is the value that corresponds to the equation of the model, which is the one that is highlighted here. So we could also get the table from the points that we see here. And there you have it. So if we compare, for example, I'm gonna just move the keyboard. If we compare the y values from 2003 from the point and then from the model, you could see that there is a little tiny excess, a little more than 290.1 million. And so that's why the point for the year 2003, I'm going to find it. It was, oops, actually, oh, here we go. So for the year 2003, you can see how the model creates that line that it is above, the line is above the point that was given to us. So if you look, for example, at, let's see, the year 2006, from the table, we had 298.4 million, and from the model, we have a little bit less. It's 0.32. So if we were to move to that year 2006, which will be here, you could see how the model, which is the line, it's below the point that was given to us. So that's another way to check. You could also get tables from Desmos. Again, you press here where it says edit, and well, I will have to do it again. Edit, and oh, I don't know how I got it done, but if you are, I believe this is for the table. I don't know how to get back to the other one. Okay, let's see. All right, let's just move on. So, to find a regression line, we could, well, first of all, those are used, they're very common to approximate a real life data, like it says here. In some instances, the model was given as an example 1, whereas in other instances, you were asked to find the model. So on example 2, we're going to find the model. And the way that is found is, if it's not with the calculator, of course, it will be by using some algebra techniques, and that will be the way that we call that process is the sum of square differences, which is the sum of the squares of the differences between the actual data values and the model values. The best fitting linear model, called the least squares regression line, is one with the least sum of square differences. So I'm going to show you how, in my emulator for the TI-84 is, my free trial has expired, and I've been trying to purchase the license, but I don't really know how to. But I'm gonna show you how you can find a video that goes with your calculator so that you could learn how to use the regression line feature from it. So one thing we could do is, I was trying to download another one from there. So I am just going to type here how to find a regression line on a TI-84, and you can see someone typed it already. And you see here the least squares regression line. So if you have another calculator, like, I don't know, maybe the TI Inspire or one of those Casio calculators. So we could do that as well, and then you could find some tips. So here's a nice video, 5-minute long. That's not too bad. So if you have one of those calculators, of course, you can find one. This is like a very common calculator that I've seen my students with. So that also shows you step by step. So if you have a TI Inspire, you could do the same thing. I'm going to go back to the TI-84. So here, as you can see, we get a lot of results. So let's say I just want a video that shows me how to. So right here, this video, 3 minutes 41 seconds. I think that's a good one. Some people refer to it, the regression line, as the line of best fit. So that's a good one too to watch. And I'll be posting the link on Blackboard so that you could have access to it. But I just wanted to show you that. Another thing, which is what I'm going to do right now, I'm just going to find not necessarily from a calculator, but from the web, from just the web. So there are several applications. Let me see if I recognize one of the websites here. Okay, let's see. Let's just try this first one, see how it looks. Okay, so we have a linear regression calculator, and so let's see. I don't really recognize it, but okay. Let's see if we can, how it will work. Well, let's try with another problem. So that is the thing we will do, and once we actually see it work, you'll be able to see something that will be denoted by the letter R, and not for radius, but for correlation coefficient. So we call it the R value, and that will be also printed as an output once you find a regression line. And so the R value could be negative or positive. However, the closer the absolute value it is to 1, so for example, here's 0, here's -1, +1, let's say this is +2, and then -2. So the closest that number is to 1, so in this interval here, the better the fit. So if that R value is, for example, let's see, let's think about a number here, like a 0.2, then it's not really a very good fit. But if it is like a 0.989, that will be a way better fit because it is closer to 1. Now, if that was negative, of course, having like a negative, I don't know, 0.96, if you enter a negative number into the absolute value, you will get a positive number, right? So with that, you can see that it's still close to 1. Oh, not 9, but 6. It's still close to 1. And so that's why we use the absolute value, just so that we can include the negative correlation coefficients and the positive ones as well. All right, so we have here, and we're going to use this example to find the regression line. So example 2, it talks about we have some data in the table, and it shows the input is again the year, and the output is going to be denoted by the letter E, and these are the number of enrollees for Medicare from 2003 to 2010, and this is also in millions. So it says here to construct a scatter plot that represents the data and find the least squares regression line for the data. So a scatter plot is going to be a graph that will not be connected. So, it just will be like a whole bunch of points. That's what we have a scatter, that will be the graph. And so the regression line tool is going to find the best line that will fit most of those points, and we will be doing that with the computer. But of course, you're free to use your calculator after you learn how to do it. Okay, so I'm going to leave this window open. Okay, so I'm going to be entering the numbers here, and for my x values, I'm going to enter one number per row. So I'm going to go from 3 to 10. Oh, I'm not typing. Okay, and then here I'm going to type the number of people with Medicare who enrolled in that particular year. So that's going to be 41.2, enter, 41.9, enter, 42.6, enter, 43.4, enter, 44.4, enter, and 45.5, enter, and 46.6, enter, 47.5, enter. And just make sure that you have the same number of outputs as you do for inputs. And now let's see what will happen if we click here, calculate the regression equation. And oh, okay, so it does look nice. I like it. And you could see here, actually I'm going to move my window. So we have the table that we enter, and then here is the graph, and I really like how it's showing us both the points that come from the table that we enter, and it also shows us the line. So that's perfect. We have both. The regression line is the line in blue, and then we have the points. We have the equation, and here in the calculation summary, you could see, I don't see the correlation. Let's see, let's zoom out a little bit. Huh. I don't see the correlation coefficient. So maybe this might not be a good one to use in case you're asked to find the correlation coefficient, but just remember you could we had several options. So let's see how close it is to the one from our notes. And we have that here. Okay, not that one, that one. Okay. So we have for our equation, we got here that value. I'm gonna copy paste it so that we could put it on our notes. Okay, so let's do that here. Just need to adjust this. Okay, and let's just enter that here. Paste. Okay, so we have it there, and there's the link for it. Okay, so now let's look at it, and let's look at the numbers. So you could see how for the slope, which is the coefficient of x, this one is a little more detailed, the one that we found with our model, but if we had to round to 2 decimals, it will be the same, 0.92. And then for our y-intercept, again, if we had to round to, let's say, 1 decimal, it will be the same, 38.2, which is what we have here for the y-intercept. And so, yeah, that's just how easy it will be. Now, if we look at the next slide, it has the collection of outputs for both. The ones that came from the table are here on the left. Those are coming from the table. And the other ones are coming from the model. Oh, and this one has the correlation coefficient, so that's good. And as you can see, it's very close to a 1. So we could consider that the model is a good fit. Okay, so now the next objective of this section is direct variation, which is very easy to find, and it is nothing but the like a linear function. And so the two basic types of linear models. So we study in section 1.4, I believe, the slope-intercept form y equals mx plus b. It's right here. And with the linear direct variation, the model becomes a little simpler because we consider the y-intercept to be equal to 0, meaning that it will be the point 0, 0 or at the origin. So that's why we don't see a number here, it's just a 0. So that is the equation that we're going to use to find the direct variation. And it will be a variation that where the letter K is representing the slope. If we look at linear variation as a linear function, K will be the same as the letter M here, which is the slope, or we also call it the rate of change. All right, and we could call it, we could say y is said to vary directly as x. So the direct variation part, we will be using the word direct, or we could say to be directly proportional to x. So here are some statements that are equivalent. So we already went over y varies directly as x, or y is directly proportional. And then we can also be given the equation for direct variation, and that here the constant k will tell us the constant of variation, that is what it represents, or also known as the constant of proportionality. So let's go ahead and do an example. Example 3, and it says, in Pennsylvania, the state income tax is directly proportional, so that is our key, to the gross income. So let's assign some variables. So y is going to represent the state income tax, the amount, I guess, in dollars. Yeah, it's not a percent. State income, because it could also be a percent. And then the letter X is going to represent the gross income. Okay, so it says here, you are working in Pennsylvania and your state income tax deduction is $46.05 or $46.05 for a gross monthly income of $1,500. So what we need to do here is substitute our values. So here we have X is equal to 1,500 or 1,500, and Y, which is the income tax, it will be 46.05, like that. So what we're going to do is use the model for direct variation, which is y equals kx. And here what we're going to do is substitute x with a 1,500 and y with the 46.05. So 46.05 will replace y, and then k, we don't know that yet, and then we know that x is equal to 1,500. So what we need to do here is we're going to find k. And we know how to find it because the 1,500 is simply multiplying to k, so we are going to divide. Okay, and we will get that k is approximately 0.0307. So that will be the constant of variation or the constant of proportionality. Now that we know k, we know that the model for that will be written here, like the equation that you see written there. So it will be y equals the constant of proportionality and then x, which is the gross income. Another type of direct variation could also be the direct variation as an nth power, with n being a real number. So for example, as the second power, the third power, the fourth power, the fifth, and so on. So in this case, we have to the second power, but we also have direct variation. So we know it's direct variation because of the constant pi. And then we know the power of another variable, and so that will be the exponent of the radius. And of course, you recognize this is the formula for the area of the circle. So the area is directly proportional to the square of the radius. So here, the first variable that is mentioned, that will be the one that goes in front of before the equal sign, And I guess you could, if you know, if you see words like is or was, that will be the equal sign. So another ways to refer to direct variation as the nth power, of course, we have y varies directly as the nth power of x, or y is directly proportional to the nth power of x. And then, of course, we could also have the equation where k is representing the direct variation, and then here the n is representing the power for which the other letter or variable will be raised to. So let's try an example of a direct variation as an nth power. And we have here the distance a ball rolls down an inclined plane is directly proportional to the square of the time it rolls. So let's go ahead and you define our variables first. So we're going to use d for distance, the distance that the ball rolls down the inclined plane. And then we're going to use t as the independent, which will be time. And the units will be seconds. The units for distance here will be in feet. So this is the dependent. The distance depends on the time that the distance traveled by the ball. So at 0 seconds it will be there, at 1 second it will be there, and you could see here at 3 seconds it will have already traveled 70 feet. Okay, so first let's write an equation relating the distance traveled to the time. So we're going to use the model d equals the constant of proportionality, because it's direct variation, times the time, but the time must be square. So it will look like that. Now we're going to use the information given to us. So we see that during the first second, the ball rolls 8 feet. So that says that at t equals 1, the distance will be 8. So if we substitute that d, we substitute that with 8, and then k, that's what we're looking for, and then t is substituted with a 1, so this will be 1, and then of course we have to square it, and what we're looking for is k. We need to find that constant before we can write down the model. So here's pretty easy because we just have 8 is equal to, and then 1 squared is just equal to 1. So it will be 1k, or in other words, 8 is equal to k. So now that we know that, we're going to use the equation that I have here, and we're going to leave it like that, but now we're going to, I mean, not like that, but what we're going to replace now is what we found for k, which is the number 8. So 8 and then t squared. So it's just d equals 8t squared, like that. Now for part B, the question says, how far will the ball roll during the first 3 seconds? So now the question says, when t is equal to 3, what will be the distance? So now, for this is like a two-part question, so, or two-part problem. We're gonna find the value of d by substituting t equals to 3 seconds. So here D will be equal to 8 times, first we have to square the 3 because of order of operation. So 3 times 3 is equal to 9. And then finally D is equal to 8 times 9, which is 72. And the units will be in feet. So that's how you find the answer. That's the answer for part B. Okay, now in examples 3 and 4, the direct variations are such that an increase in one variable corresponds to an increase in the other variable. That's what we see with direct variation. So here I just want to point out that the 1/5 that you see flying here, that shouldn't be there. That should be here in front, multiplying f. And that will be like the constant of proportionality, 1/5. So the increase in f results in an increase in d, even if the constant k is less than 1. They will still both be increasing. Now, you should not, however, assume that this will always occur with direct variation, okay? For example, in the model, y equals negative 3x will be an increase in x result in a decrease in y, and that is because the constant of variation is negative 3, which is less than 0. So if the constant is greater than 0, we will see that increasing behavior. But if it is less than 0, we will see the decreasing behavior for the dependent variable. Okay, so let's move on to the next type of variation. This is called inverse variation. And inverse variation will be considered like a division. We will still have the constant of proportionality, but the other variable will be dividing that constant. Like that. And the words that we could use to represent that is y varies inversely. That's your keyword, not directly, inversely. That's how we know that the other will be dividing, the other variable. And we could also say y is inversely proportional to x. So we could also, to the fact that this is an inverse variation, we could also use an exponent there. And then that will be something like of that form. So it will be something like y varies inversely as the nth power of x. So that's where the power or the exponent will be located at. So just like we could have an exponent with direct variation, we could also have it with inverse variation. So let's go ahead and do an example. Example 5. It says a company has found that the demand for one of its products varies inversely as the price of the product. Okay, so we don't have an exponent here. So we're going to use the model y equals k over x. And let's say that y is going to be the demand of the product, like how much people want it, and then x is going to be representing the price of the product. We could choose other letters, like for example I could have used D for demand and P for price, but let's just keep them with y and x. However, on WebAssign you might be told what variable to use, okay? So we're going to use the information provided to us. It says here, when the price is $6.25, the demand is 400 units. So what we're saying here is that when X is equal to 6.25, the demand, which is Y, is equal to 400. So we're going to be substituting X and Y to find K. So let's do that. So instead of Y, we use the 400. And then instead of X, we will use 625. So for K, we see that the 6.25 is dividing to K. So if we take that across the equal sign, it's going to be doing the inverse operation, which will be multiplication. And so then we're going to get that K is approximately equal to 2,500 or 2,500. So the model, based on the description of inverse variation, will be Y is equal to 2,500 divided by the value of X. And with that, we can answer the second part of the question, which is approximate the demand when the price is $5.75. So if the price decreases, what will happen to the demand? Would it go up or down? So in this case, we are looking for Y when X is equal to 5.75. And that's what I'm substituting here. And so Y, which is the demand, is going to come from us dividing that 2,500 divided by 5.75, and that will give me 434.78. so let's round to one decimal place, so it will be 0.8. So you could see the demand actually went up, is higher than 400 because the price decreased. But if we were to increase the price, then the demand will decrease. So just as a quick example, if the question was, what is the demand if the price goes up to, I don't know, let's say $7.50? And we still use the same constant for K, and that will give us 333.3. So you see the demand went down when the price increased. Okay, example 6, combined variation. So in this case, we're going to have a gas law states that the volume of an enclosed gas varies directly. So we have here varies directly as the temperature and inversely as the pressure. So right there we have two types of variation, direct and inverse. So let's see. We will be using volume is the output, and it says varies directly, so we still need a K there. As the temperature, let's use capital T for temperature, and it says inversely as the pressure, so the pressure, let's use capital P to denote the pressure. So the information provided to us is that the pressure of a gas is 0.75 kilogram square. I'm sorry, kilogram per square centimeter. So that will be a unit of pressure. When the temperature is 294 Kelvin degrees and the volume is equal to 8,000. So we're going to substitute volume with 8,000. We will be substituting the pressure with 294, and we will substitute the, okay, so I said this wrong. The temperature is gonna be here because the temperature is varying directly, so it goes on the numerator multiplied by the K, by the constant K. Now, K here is representing it's for units, and it's Kelvin, degrees Kelvin. And so that's for temperature. It's not the same as this K here. This one is like a lowercase. Okay, and then the pressure is going to be substituted here. So we're going to do that. So instead of volume, we enter 8,000. And then we're going to solve for K. The temperature is 294. And the pressure is equal to 0.75. So to solve for K, we could do the following. We have 8,000 here. And if you notice, the 294, we're solving for K, right? So the 294 is multiplying to K. So if we take the 294 across the equal sign, it's going to be dividing. And then the 0.75 is dividing to K. So if we take that across the equal sign, it will be multiplying. So in this case, I'm going to multiply 8,000 times 0.75. And then I'm going to divide that result by 294. And so I'm going to get that K is approximately, rounding it to the nearest tenth, it will be 20.4. So the equation that we're going to use is the volume is equal to that constant that we just found, 20.4, times the temperature divided by the pressure. And that will be the answer for part A. Part B is asking us find the pressure when the temperature is 300 degrees Kelvin and the volume is equal to 7,000. So you have to be very careful about what you're substituting and what are you looking for. So in this case, pressure is the question. So let's see, and let's go ahead and start substituting what we know. So we know the volume is 7,000. We know K is, by using this equation here, K will be 20.4. And then we have the value for the temperature as well. And that is equal to 300 here. And then we're looking for the pressure. So what we got to do here is isolate the variable for pressure, because that is our question. So one thing I can do is, and actually we do have room to solve it here. And let's see, here they're solving it, first they're isolating. Yeah. So let's just solve it from here. So what we could do is multiply these two quantities. So 20.4 times 300. And that will give us that 7,000 is equal to 6,120 divided by the pressure. So from here, I can take the variable for pressure to the left side, and it will be the letter P times 7,000, the ones from here, is equal to 6,120. And so since I want to solve for P, it's going to be the 7,000 goes to the right side dividing. So now we're going to have that the pressure is equal to 6,120 divided by 7,000. And we get 0.874. And if we round to the nearest tenth, or hundredth, I should say, we will have 0.87. And the units for pressure are kilogram per square centimeter for this problem. So that is the answer right there. Okay, the next type of variation that we will cover is joint variation. And this is, if you look at the equation that we see here, we have that z varies jointly as the nth power of x and the mth power of y. So right here, the nth power of x is represented here, and then the mth power of y is here. And we have that, instead of mention direct variation twice, they are using the word jointly, and that will be the k right there, multiplying both x and y after they're raised to a certain power. So the ways to say that, of course, z varies jointly, or z is jointly proportional to x and y. If they don't mention an exponent, it means the exponent for x and y is a 1, but they might use an exponent like how it says here. Okay, and without the exponents, like we see it here, it will just be that equation. That means jointly proportional to x and y. So here for our last example is about joint variation, and we have the simple interest for a certain savings account is jointly proportional to the time in the principal. So we're going to use T for time and capital P for principal. So this formula here, we could also write it as interest is equal to the principal times the time, and then times a letter, in this case K. Now the way that this equation is actually written is pretty famous. It's with, instead of K, with an R for rate, interest rate. But let's just use K because we're doing this section, and so K is the constant of proportionality of variation. So let's see. T is the time, capital I is the interest, the simple interest, and then capital P will be the principal, which is the money that you put in at first. So it says find the interest after 3 quarters. So the information that we have here is that after 1 quarter, so I forgot to state, time for this money problems is given in years. So after 1 quarter, that means that T is equal to 1/4, or we could also use T is equal to 0.25, because that is 1 quarter. And or 3 months. The interest on a principal of 5,000. So here the principal is 5,000. So P is equal to 5,000. And then the interest, the actual interest is $43.75. So I'm actually gonna erase this here so I can do the first part of the problem there. And so we're going to replace the principal with 5,000. We're going to replace the interest with 43.75. And we're going to be replacing the time with 0.25. And we're going to do that to solve for K. So let's do this. So instead of interest, we write 43.75. And then we're going to have here, instead of the principal, that will be 5,000. And then instead of T, we write 0.25. And then we'll have K here. That's what we're solving for. All right, so I'm going to multiply these two numbers. So it's going to be a quarter of 5,000, or 5,000 times 0.25. So that will give me, I'm going to have to use the space here. Oh, well, I can just write it here. 43.75 is equal to 1,250 times K. So now this is pretty easy because all we got to do is to solve for K will be to take the 1250 to the left side. So from multiplying on the right side, it will be dividing. So it's going to be K is equal to 43.75 divided by 1250. So then K is going to be equal to 0.035. And so the answer to part A, I'm going to write it here, is going to be the equation following this model here. Is going to be the interest is equal to the principal times the time, and then the number 0.035. Or, of course, we can write it this way. Interest is equal to 0.035 times the principal times the time. That is the answer for part A. For part B, it says find the interest after 3 quarters. So now the question for part B is find what is the interest? That's our question. For the after 3 quarters. So now we want our time to be 3 quarters, 3/4, or as a decimal, it will be 0.75. And the principal, since they're not giving us a new principal, we will just take the same from here, 5,000. So we're going to substitute into the answer that we found for A. Well, there's another 0 there. Okay, so that will be I is equal to 0.035 times 5,000 times 0.75 for 3 quarters of a year. And let's see. So if we multiply those 3 numbers, I get an interest of $131 with 25 cents. And so that will be the amount of interest accumulated after 3/4 of a year, which will be like 9 months, at a rate of 0.035. That's the, I mentioned to you, that's the interest rate. So if we were to convert that to a percent, it will be like an interest rate of 3.5%. But the answer to part B was the amount of interest accumulated. So it's 131.25. So this is the last question, end of the video.